Class, this is our first screencast for the notes for chapters 6, chapter 6, 6.1, 6.2. So let's take a quick look at this electronic structure of atoms. So all you need to know about atoms can be described in one of two ways, either as particles or as waves. And we're going to focus obviously on the waves first. So to understand how an atom, or actually to be more specific, electrons, work as waves, we're going to have to know a little bit about waves to start with, which I know you guys have seen this kind of thing before. So a wavelength, you know, is from one point to another. There we go. From one point to another, the length that it takes for the wave, like how long it is. Obviously, the amplitude is how high it is. Frequency would be the number of waves passing a given point in a certain amount of time. And usually we use seconds for that time. So to be something like 10 waves per second would be 10 hertz. So you would see something that looks like this. Sorry, it's Hz for hertz. And that just means, and if you see this, seconds with a -1, that is the same as 1 over seconds, which is how we measure frequency, which we'll get into. So wavelength actually is, we use this symbol, it's the lowercase lambda, which means like we're using Greek letters, and that's just the way it is, unfortunately. So it says the number of waves passing a given point per unit of time is frequency. The waves traveling at the same velocity, the longer the wavelength, the smaller the frequency. So our speed of the wave is going to be the same for the waves that we're going to be talking about. And that speed, of course, is c, which is the speed of light. Now, when you say the speed of light, that means 7 times around the Earth in 1 second. That's how fast the speed of light is. 3.0 times 10 to the 8th meters per second. Okay, that's the speed that we're talking about. Meters, that's an M there. Meters per second, okay? So if they're all traveling at that speed, then the wavelength really determines how many waves pass a given point in a certain amount of time. So wavelength and frequency for a constant speed are related, significantly related. Okay, so let's talk about the electromagnetic spectrum. The electromagnetic spectrum is from gamma to radio waves, and notice only a very small part in here is the actual visible light. Now we measure wavelength with nanometers when we're talking about the visible region. So 400 would be a shorter wavelength, which means higher frequency, which means, and we'll get to this, which means more energy. So something like a blue light has more energy than a red light does. So notice on this end here, it's not actually blue. This would be violet. This would be our Roy G. Biv, okay, backwards. So red, orange, yellow, green, Roy G. Biv. That would be blue, indigo, and violet, okay? So notice that if you're slightly less than red, then you're infrared. If you're slightly more than violet, you're ultraviolet. Okay, that's where those two come from. Microwaves is less than infrared, and radio waves is at the lowest frequency. So radio waves actually means that they can bounce off the ionosphere of the Earth and come back down to Earth, and they pass right through you, and they do no damage whatsoever. Microwaves, you may have heard of microwaves before because of course, the microwave oven. And microwaves heat up. They heat up a frequency that is relatable to water, which is why it heats your food, because all food has water in it. And if it doesn't, then it doesn't heat up. Okay, so let's keep moving. So the nature of energy. So the wave nature of light does not explain how an object can glow when its temperature increases. Max Planck explained by assuming the energy comes from packets called quanta, which is exactly what happens. So light has energy in packets called quanta, which is not what obviously people thought beforehand. They thought light was continuous like a wave, like waves on an ocean, when in fact the energy that comes from a wave travels in packets, which is odd, but that's how it works. Einstein used this assumption to explain the photoelectric effect. The photoelectric effect is when you shine a type of electromagnetic radiation with high enough energy, which means high enough frequency or a low enough wavelength, on a piece of metal, and it kicks electrons off that metal. And that can happen, and that's what the photoelectric effect is. This is actually something that Einstein was given, I believe he got the Nobel Physics Award for this work. So he used Planck's theorem about packets of energy, or quanta, where h is Planck's constant. Take a look at that number, times 10 to the negative 34th. We're talking about a very, very, very small amount of energy that this quanta is representing. It's proportional to frequency. This E right here is energy, so this would be energy equals Planck's constant times, I'm going to say PC for Planck's constant times frequency. And that's what you're looking at with that. Frequency, like that. Okay, Planck's constant, like that, is this number, and then times whatever the frequency is. Remember that frequency is in hertz. So anyway, let's keep moving. Although I think that might be it. Excellent. Now we're getting into, well, we can still talk about this. So c right here is the speed of light, is times wavelength, wavelength times frequency, like this. So that would be wavelength, as you saw in nanometers. We would have to change that to times 10 negative 9 meters, because our frequency is going to be measured in per seconds, which is what, if you remember, when I wrote up there 300 times 10 to the eighth, not negative eighth. Let me get rid of that and do that over again. 10 to the eighth, that is meters per second. And our meters comes from our wavelength, and our per seconds comes from frequency. And that's how it all works together. And then we talked about that one already. Good. All right, I'm going to stop there. So this screencast doesn't go on too long. So take those notes and submit them, please. Thank you.